Now this is about conductors. An insulator such as glass or rubber has bound electrons. In a metallic conductor, one or more electrons per atom is free to move around the material. In liquid conductors like salt water, if the ions move, it is the ions that move, sorry. A perfect conductor would contain an unlimited supply of free charges, which is unrealistic. But now properties of the ideal conductor. Our electric field is zero inside the conductor. Why? Because if there were any field, then free charges would move. Now what happens when you put a conductor in an electric field? We'll get this relation where our electrons are pushed to one side, leaving a positive charge on the other side. Now the field, we will derive three positive charges, right and negative charges on the left, and when you come to the edge of the material, the charges pile up. Thus it induces an induced charge produce an electric field E1 in the opposite direction of E0. Now the fields cancel the original field charge, so will flow until the cancellation is complete, and the resultant field inside the conductor is zero. Now for ρ equals 0 inside the conductor, which follows from Gauss's law here, if our electric field is 0, so is ρ. Sorry, there is still charge, but exactly as much plus charge as minus, so the net charge density inside is 0. Now where any net charge resides on the surface, a conductor is an equipotential, for if A and B are any 2 points within or at the surface of a given conductor, then our potential is given here, where our V of A equals our V of B. Now where E is perpendicular to the surface outside of the conductor, so charge will move around the surface until it kills off tangential components. Now surface charge and force on a conductor. Example, because our electric field is 0 inside a capacitor, I should have mentioned this becomes a capacitor then. Boundary conditions require the field be outside to be this in terms of the potential here. Now this enables you to calculate surface charge on a conductor. If you can determine our electric field or potential in the presence of an electric field, a surface charge will experience a force per unit area. If F is our sigma multiplied by electric field charge multiplied by the electric field, but there's a problem for the electric field. It is discontinuous at the surface, as we went through before. So should we use electric field above, electric field below? We should use the average of the two here. Now a little picture here. The total field consists of two parts that attribute to patch itself, and that due to everything else, other parts of the surface and outside. Now E equals our electric field from our patch, and plus our electric field of all the other stuff. And the patch cannot exert a force on itself. The force on the patch is due exclusively to electric field of the other, and this suffers no discontinuity. The discontinuity is due to the charge on the patch, which puts out a field given here on either side pointing away from the surface. Thus our electric field above is we're adding this term in here. Now electric field below will simply subtract that. So an electric field over is 1/2 above and below, which equals the average. Now the field is 0 inside and it's this outside, so the average is simply 1/2 of this, and the force per unit area is given here. This amounts to an outward pressure on the surface tending to draw the conductor into field regardless of sign of our charge. Now the pressure in terms of the field is given by this.